Welcome to the deep dive. We're here to pull out the key stuff from complex topics so you get the insights fast.
Yep, making you smarter, quicker.
Today, we are diving headfirst into large language models, LLMs, the tech behind chatbots, all that creative AI stuff.
And we're asking a pretty fundamental question.
Mm.
What are the, hidden rules? How do these huge models actually learn?
It's like getting the cheat sheet, isn't it, for training these incredibly complex things.
Exactly.
And you, our listener, want to get the core ideas without drowning in technical jargon. You want the knowledge efficiently.
And that's what this deep dive is all about.
Right. So our guide today is a research paper, and it's got this pretty intriguing title, Neural Thermodynamic Laws for Large Language Model Training.
Okay, yeah, thermodynamic laws. Sounds physics heavy, maybe a bit intimidating.
It does, but stick with us because the connections it makes are genuinely surprising.
The main idea, the real hook, is this parallel the paper draws between how LLMs train and the basic principles of thermodynamics. Heat, energy, entropy. Stuff you normally think about with engines or, melting ice.
It seems worlds apart.
Right. But concepts like temperature and entropy, they sort of naturally emerge when you analyze the LLM training process. It's pretty wild.
Amazing. So that's our mission for this deep dive. Let's unpack these links.
And pull out the practical stuff.
Yeah.
Especially around learning rates.
Ah, yes, the learning rate schedule. Super crucial for actually training these models effectively. How fast should they learn and when?
Okay, let's get into it.
So where does the paper start?
It starts by describing the shape of the learning process. They call it a river valley structure.
River Valley, okay.
Picture this landscape, right? You got these wide, pretty flat rivers. That's where learning is slow, but it's steady progress.
Okay, moving along the riverbed.
But then, bordering these rivers, you have steep valleys. And in these valleys, the model's performance, like its accuracy, it bounces around. A lot. Fast fluctuations.
Got it. So sometimes you're making smooth progress on the flat part, the river, but you're always near these steep bits, the valleys, where things can suddenly get much worse, or maybe slightly better, but it's noisy.
Precisely. It's like hiking. Yeah. Easy trail, then suddenly you're near a cliff edge. Metaphorically, of course.
Right.
For the model's loss function.
Right. Loss going up and down quickly.
And here's a really neat idea they introduce. They split the overall learning, the total loss, into two pieces.
Okay.
There's the slow loss. That's your progress along the river, your main trend.
The steady improvement.
And then there's the fast loss. That captures all that bouncing around within the valley, the noisy part.
Ah, okay. And this is where thermodynamics starts to creep in.
This is the bridge. They propose that the slow loss, moving along the river, it's like a macroscopic property in physics.
Like the volume of a gas in a container, something big picture.
Exactly like that.
Yeah.
And the fast loss, the fluctuations in the valley,
Yeah.
that's analogous to the microscopic stuff. The tiny degrees of freedom, like individual gas molecules vibrating, bumping around.
Wow. Okay. So the noise in the training data, the step-by-step updates, that injects a kind of random energy.
Yeah, kind of thermal energy, leading to those fast fluctuations.
This immediately brings up a huge practical issue for training, doesn't it? The learning rate.
Totally. How do you pick it?
You'd think, okay, high learning rate, go fast along the river, make progress.
Right, but that high learning rate,
It makes the bouncing in the valleys worse, more chaotic.
it can, yeah. Bigger fluctuations, more disruption potentially. But then, if you go with a really low learning rate,
Things might be stable in the valley, less bouncing.
but progress along the river slows to a crawl. Like wading through treacle.
So it's this fundamental trade-off, speed versus stability.
That balancing act is really central to figuring out the best way to adjust the learning rate over time, the schedule.
Okay, so we have this river valley picture, we split the loss. How do thermodynamics concepts like temperature actually map onto this?
This is where it gets really cool. The paper argues and shows evidence that the learning rate itself,
The number we set to control the update size.
yeah, that parameter, eta, it can be directly interpreted as an effective temperature of the neural network system during training.
Temperature. In an AI model, that feels like a huge leap. How?
Okay, so it connects to something called the equipartition theorem from physics.
Right, I vaguely remember that. Energy distribution.
Sort of. In simple terms, it says that for a system in thermal equilibrium, energy gets spread out equally among all the ways the system can store it, provided those ways are like quadratic. Think simple springs.
Okay, great.
So in the LLM context, this thermal loss, the fast valley fluctuations becomes independent of how sharp or steep the valley walls are.
Wait, so whether the valley is a sharp V shape or a gentler U shape, the amount of energy, the thermal loss from bouncing around is the same?
As long as the temperature, the learning rate is the same, yes. It's like the energy of a vibrating atom doesn't depend on how stiff its bond is, just on the temperature.
That's unexpected.
Isn't it? And they backed this up. They looked at GPT-2 training,
A real model.
a real large model.
Yeah.
And they found a clear linear relationship, a straight line, between the final validation loss, the errors the model makes, and the minimum learning rate used during the final cooling down phase of training.
Wow. So lower final learning rate directly meant lower final error in a straight line.
Exactly. Which really strongly supports this idea that the minimum learning rate is acting like a final temperature. You cool it down, you reduce the thermal noise or error.
And did they quantify those valley directions, the steep bits?
They did. They estimated that for GPT-2, it's only about 4% of all the model's parameters that correspond to these sharp valley directions.
Only 4%. That's surprisingly small.
It suggests that most of the parameter space, most of that vast landscape inside the model, is actually relatively flat. It's mostly that river structure.
Okay, this leads us naturally to that cooling down phase you mentioned. Learning rate, annealing.
Right, annealing. Just a fancy word for gradually decreasing the learning rate over time. It's a standard practice.
But how you decrease it matters, right?
Immensely. The paper digs into finding the optimal way to anneal, the best schedule to reduce that thermal loss, those valley fluctuations, most efficiently, and end up with the lowest possible error.
So designing the perfect cool-down sequence for the learning process.
Exactly. And based on their thermodynamic analogy in math, they derive a specific formula for this optimal decay.
Okay, what's the gist?
The key takeaway is that the learning rate should decrease roughly inversely with time. It follows a specific curve, 1 plus what's 2 think, where the is some characteristic time.
Inversely with time. But what's really weird, you mentioned something about the start?
Yes. This is super counterintuitive. Their optimal schedule has a jump, a discontinuity, right at the beginning of the decay phase at TO0.
A jump. What does that mean practically?
It suggests that the best thing might be to instantly cut your stable learning rate roughly in half when you start the decay, not smoothly ramp it down.
Whoa. That's definitely not what most standard schedules like cosine decay do. They're smooth.
It's not. Their logic is that starting the decay at half the stable rate is somehow the most efficient way to begin removing that thermal loss quickly. Sticking with the high rate is bad. Dropping instantly to 0 is also bad, maybe impossible.
Yeah, you mentioned that dropping to 0, it's not ideal.
Their theory suggests trying to anneal all the way to 0 learning rate would actually take infinite time. You'd never quite get there and eliminate all the thermal loss.
Which makes practical sense. You have to stop training eventually.
Right. You aim for a small, non-zero minimum learning rate.
They also draw another physics comparison here, right?
Yeah.
With sudden changes.
Yeah, to Fourier's law of heat conduction. If you suddenly change the learning rate, like that proposed jump, or any sudden change, the thermal loss doesn't instantly adjust.
It takes time to catch up.
Exactly. It decays exponentially towards the new equilibrium level set by the new learning rate. Like a hot coffee cooling down to room temperature, it's not instant.
And they tested this optimal schedule idea.
They did. They used simpler toy model experiments to confirm that their derived schedule actually worked better than others.
Did they account for the valleys not being perfectly symmetrical? Like different sharpness in different directions?
Yes, they looked at anisotropic landscapes, which is more realistic for real LLMs. And it confirmed the basic idea, but showed, unsurprisingly, that progress is slower in the flatter directions within the valley. It just adds complexity to the optimization challenge.
Okay, this is fascinating. But there's another concept in the paper, entropic forces, that sounds even more abstract.
It does, but let's break it down. Remember those fast fluctuations, the bouncing around in the valleys?
The fast loss.
All that jiggling can actually exert an average sort of effective push or pull on the slow progress along the river.
The fast dynamics influence the slow dynamics.
That's the idea. This average influence is what they call the entropic force. It's like the average gradient or slope of the fast loss, but projected onto the slow direction.
So the noise isn't just noise, it can actively steer the learning.
It can. And crucially, this entropic force tends to point towards regions where the valley is wider or less sharp.
Wider valleys.
Why there? It connects to entropy. In this framework, entropy is related to the volume of the accessible space, which is larger in wider valleys. Systems tend to move towards higher entropy. So wider valley, higher entropy, the force pushes that way.
They link sharpness and entropy.
Yeah, entropy here is kind of like minus the log of the sharpness. Less sharp, higher entropy. It echoes Boltzmann's entropy and even touches on the third law of thermodynamics.
Wow. Okay, but this force can be bad, right? Entropic trapping.
Exactly. That's the potential downside. This entropic force could push the model away from the direction it needs to go along the river to find the actual minimum loss.
So even if the bottom of the river is still going downhill, this force could push you sideways or even backwards.
It could hinder progress. The fluctuations themselves create a force that traps you, preventing you from reaching the best possible solution that lies further down the river.
That's a bit scary for training. Did they find evidence of this in real LLMs?
They tried to probe it in GPT-2. They compared training runs using different learning rate schedules, but ensuring the total amount of learning, the sum of the learning rates over time, was the same.
Clever way to isolate other effects.
Yeah. Their findings were subtle, but they suggested slightly negative entropic forces in the early stages of GPT-2 training.
Negative, meaning?
Meaning the force was actually pointing towards narrower valleys, slightly hindering progress initially. It wasn't a huge effect, but it was measurable.
Okay, so let's try to pull all this together. The learning rate isn't just one thing.
Not at all. The paper really highlights three distinct roles it plays.
Right.
First, it's the temperature. It controls the scale, the width, of those fast, random fluctuations in the valleys, like Gaussian noise width.
Okay, second.
Second, it sets the magnitude of those entropic forces we just discussed. Higher learning rate, potentially stronger entropic forces.
And third?
And third, it's still the basic thing we always thought it was. The step size. It controls the overall time scale, how quickly we move along the landscape, especially the river.
Temperature, entropic force strength, and step size, all packed into one parameter.
Yep, which explains why tuning it is so critical and often so tricky.
So what does this thermodynamic view tell us about achieving the best final performance, minimizing that final error?
They summarize the final loss nicely. It's basically determined by three main things.
Which are?
1, the loss you'd get just from the slow dynamics and the minimum learning rate you reach, E, D, Meeman. Think of this as the baseline error determined by how much you learned, D, the integral of E, and how cool you got Meeman.
Okay, baseline error.
2, a correction due to those entropic forces.
Gotcha.
Entropic, did they help or hinder?
Right.
And 3, a correction related to how efficiently you annealed the learning rate.
Yeah.
Did you cool down optimally?
So final baseline plus entropic plus IANL, roughly.
That's the essence. And their analysis suggests that to really drive down that final loss, the main levers you have are reducing that minimum learning rate, even as much as possible.
Getting colder.
And potentially increasing the total learning done during the stable phase, that D term, maybe by using a higher stable learning rate if it doesn't cause instability.
Ah, so maybe being a bit more aggressive with the initial stable learning rate could actually lead to a better final result, counterintuitively.
As long as it's stable, yes. More exploration early might help find a better river path, and then you cool it down effectively.
This deep dive has really shifted my perspective. It's not just empirical trial and error with learning rates anymore.
Exactly. This thermodynamic view gives a mechanistic understanding. Why do certain schedules work? What are the underlying forces and trade-offs?
We've seen the river valley landscape, the emergence of temperature,
The optimal annealing schedule, even with that weird jump.
and these subtle but potentially crucial entropic forces. It's much richer than just turn the knob.
Absolutely. It provides principles, not just recipes.
It really makes you wonder, doesn't it? Like, could these same thermodynamic ideas apply to other kinds of machine learning? Not just LLMs.
That's a huge open question. How general are these laws?
And how can we use these insights? Could we design entirely new optimizers based on thermodynamic control?
Potentially. Optimizers that explicitly manage temperature and maybe even counteract entropic trapping.
And what about those entropic forces over really, really long training runs? Do they become more dominant? Could they fundamentally limit how good these models can get?
Lots to explore there, definitely.
It leaves you with this final thought, kind of provocative. The process of training these incredibly complex artificial systems, maybe it really is governed by laws that echo the fundamental physics of the universe around us.
AI meets physics in a deep way. It's a fascinating place to be looking.
Definitely something to chew on. Thanks for joining us for this deep dive.